So let's try another example using the Moivre's theorem. So this one, again, the examples are uh, they're gonna be having directions in different formats. That way you can kind of see all the different ways that it could be asked to do the same thing. Okay, that you can be asked to do the same thing. So this example 3 here says find the square roots of 4 parentheses cosine of 90 degrees plus I sine of 90 degrees and express answer in trigonometric form. So here, again, since they want it in trigonometric form, you don't have to actually evaluate. You can just, you don't have to have it in A plus BI form, which is nice. And honestly, it's already nice too because they already give it to you in trigonometric form. Like in the previous problem, it was given in complex form, complex as a complex number, and then you had to write it in trigonometric form and then apply the definition. But here you're already given, you already know your r and you already know your theta, which is so nice. So and here they want us to find the square roots. So square roots, again, that would be 1 over n. Okay, so let me just remind you. Remember that square roots are, again, the square root, let's just call it, of x, or you can write it as x to the 1/2 power. And so here my n would be 2 because we're looking for the square roots. Square 2, all right? And so that means that implies that n is equal to 2 in this case. Alrighty? So we know that n is equal to 2. So we also know that r is equal to 4, and we know that theta is equal to 90 degrees. So all we have to do is plug it into our previous theorem, the nth roots theorem. So let me just remind you of what that theorem says. And so it says that if you have r to the 1/nth power, okay. So if you want to find the nth root, in this case we have the square root. This would be cosine of your theta plus 2 pi k, or 2k pi, doesn't actually matter the order, all over your little n. That looks like an H, little n, and then plus I sine of that same quantity. Theta plus 2 pi k all over little n. All right, and so again, this formula here helps us find all of the different roots to this solution. So again, I'm just going to plug everything in. And so we get 4 raised to the 1/2 power, because again, my n is 2. And then we're taking the cosine of, and since we're given in 90 degrees, then I'm just going to work with degrees. And so my theta is 90 degrees. And so instead of having 2 pi k, I'm going to have 360 degrees k all over little n, which my little n is 2. And then plus I sine of 90 degrees plus 360 degrees k all over 2. And before I actually plug in values of k, the best way to proceed is to actually simplify this a little bit, because it's a little bit messy right now. Maybe we can clean this up, this quantity that's inside of the cosine and the sine. And so let's simplify this a little bit. So 4 to the 1/2 power is the same thing as the square root of 4, which is just 2. So that's going to be 2 times, and then cosine. And so remember, this 2 here is dividing both of these terms. So 90 degrees divided by 2, that's just 45 degrees. And 360 degrees divided by 2, it's 180 degrees k. And so again, all those angles were cut in half. And so again, the same thing is going to be on this side. So I plus sine of 45 degrees plus 180 degrees k. So notice that it looks so much nicer now. And so it's going to make it easier for us when we plug in values of k. So now let's go ahead and plug in values of k. All right, so k is equal to 0. Actually, up to what number are we going to go to? So again, it goes k goes to n minus 1. N is 2, so n minus 1 would be 1. All right, so just again, let me write this down. So k goes from 0. It goes from 0 all the way to n minus 1. But again, n here is 2, so it's going to go up to 1. So k is going to be 0 and then 1, which makes sense because again, we have the square roots, which n is 2, so we're only going to plug in 2 values for k. So k is equal to 0. That's going to be the first one. So we get 2 times cosine of 45 degrees. And again, plus, here, I'll write it all out. 180 degrees times 0, which is what we're plugging in. And then plus I sine of 45 degrees plus 180. Oh, that looks a little messy. Plus 180 degrees times 0. Right? Again, this 0 here. This is my 0 here. Okay, I'm just plugging it into there. All right, so I'm gonna simplify this. So I get 2, and then this is just cosine of 45 degrees plus I sine of 45 degrees. And again, it's asking us to leave it in trigonometric form. So again, it's asking us here. I've been using that color for other things. So I'll just use this one. It's asking us to leave it in trigonometric form, and so that would be the final answer. If it asks for complex number or like a plus bi, then we would have to simplify this. But again, it's asking to express in trigonometric form, which is nice because that reduces our work here. So the next thing is plugging k equals 1. That's the last one. So k equals 1. So we get 2 cosine of 45 degrees plus 180 degrees, because now k is equal to 1, plus I sine of 45 degrees plus 180 degrees. Okay, so let's just clean that up a little bit. And so we get 2 times cosine of, here's going to be 225 degrees plus I sine of 225 degrees. Right? And so again, these are the square roots of that complex number. So here, or maybe I'll write it down. So the square roots of 4 cosine of 90 degrees plus I sine of 90 degrees are 2 cosine of 45 degrees plus I sine of 45 degrees and 2 cosine of 225 degrees plus I sine of 225 degrees. So I'm going to graph them again just for funsies. And again, just to show you guys that that these are, again, when you graph these two square roots, they're going to be equal distance from each other. So I'm making it too large. Okay, so here we go. The first one I'm going to call, again, I'm going to call this one's A, this one's B. All right, so my R is 2 and my angle is 45 degrees. Let me go here. 1, 2, 1, 2, 1, 2, 1, 2. And again, it's not drawn to scale, but again, it gives you a little bit of an idea. And so my R is 2 here, so it's going to be somewhere around this radius here, and it's 45 degrees, so it's going to slice the first quadrant in half. So it's going to be somewhere here. That's going to be the length too, somewhere in here. Because again, radius 2 would give me a circle here, so maybe I'm a little bit high up. So let me just, so this would be, that's where that point would be. That would be A here, and then B going to be at 225, again at 2. So again, the distance from here to here has to be 2. So I'm going to again use a circle here, and then 225 is going to be in quadrant 3, and it's slicing it in half as well. And so here, that's going to be my point there. And so notice that here as well, that these two solutions are equal distance from each other. They're actually 80 degrees, 180 degrees apart. Okay, so again, I'm going to write here that's just checking graphically. Just checking graphically. Smiley. All right. Okay. Let's try again another problem, another format of asking you to do the same thing. Okay. And so the problem says find all complex solutions to x to the third power plus 125 is equal to 0. Okay, so here it says find all the complex solutions to x to the third power is equal to 125. So okay, I'm just gonna treat it as a regular problem. And so we have x to the third power plus 125 is equal to 0. I'm gonna try to solve for x here. So I get x to the third power is equal to negative 125. And then I'm gonna take the cube root again to isolate x, and so I get x is equal to the cube root of negative 125. Okay, so now at this point, notice that we have a negative inside this square root, and we actually know one of the solutions. One of the solutions is just a real solution. We know that if we know that negative 5 is a perfect cube, right? So one of the solutions here, so one real solution is x is equal to negative 5. Because again, negative 5 to the third power is negative 125. But we don't know the other solutions. Because again, remember, this is a polynomial of degree 3, meaning that we're going to have 3 solutions. And some of them are going to be real, some of them are complex. So we know one of the real ones. That means that we're missing 2 other solutions. And so we're going to actually be able to find that by taking, again, the by using the previous theorem that helps us find the rest of the roots. Okay, so again, one of the solutions to this equation is x equal to negative 5. And again, I'm just going to use the theorem. The theorem is going to generate all the solutions anyway, but I'm just letting you guys know that we can already see that one of the solutions is negative 5, but we still have to find the rest of them, which are going to be complex. So we're going to have to use that theorem. And so again, let me just remind you of the theorem. It says that we have r to the 1 over nth power, and again, it just depends. In this case, it's going to be the third power, 1 over the third power here, because again, we have the cube root, times the quantity cosine of theta plus 2 pi k all over n plus I sine of theta plus 2 pi k over n. Right, so again, this is by that theorem, the nth roots of a complex number. So again, this would be equal to whatever in this case would be x. X is equal to, again, all the solutions generated by this equation. And again, I'm going to show you guys that x equals to negative 5 is going to end up being one of these solutions. Okay. And so let's actually figure out, again, the complex number here that we're working with doesn't really look like a regular complex number. So for example, this here is going to be x is equal to the same thing as negative 125 to the 1/3 power. This here is actually this is the complex number that we're talking about. And it doesn't look like in that form a plus bi, right? But the imaginary part is actually 0. And so this is the same thing as having negative 125 plus 0i to the 1/3 power. Alright, and so here my complex number, like I said, is negative 125 plus 0i. And again, we're finding the cube roots of that complex number. So let me just write that down just in case you're a little bit confused. So my complex number is negative 125 plus 0I. Okay, so again, that's my complex number there. And so again, in order for us to use that theorem, we have to write our complex number in trigonometric form, or we have to find r and its theta. So again, that's step one. So let's write it in trig form. So let me, again, I'm going to okay, so trig form here, we're going to do r, or modulus, is equal to the square root of the real part, negative 125 degrees, well, not degrees, 100, negative 125 squared, plus my imaginary part, which is 0 squared. And so I get the square root of 125. So the square root of 125 squared, which is just going to be 125. And if I graph it, it's going to make sense because, again, if we plot this this complex number um, is going to be on my horizontal axis, which is my real axis, which is negative 125. So this here is just going to be negative 125 here. And then notice that the distance from the center to that point is just 125, which makes sense that r is 125. And the angle here, we don't have to do that much work for this problem actually, because again, the angle in standard position is going to be 180 degrees, or pi here. Okay, so that's going to be my theta. So that made it a little bit easy here as well. So theta here is going to be 180 degrees, or we could use radians in pi. All right. So now now we have r and we have theta. So let's just plug it into our formula here, or theorem definition here. So plug in values. All right, and so we get x, again, that's going to be our solution. X is equal to, and r here is 125, so we have 125, and then again, my n is 3, so 1 over 3, because again, we're looking for the cube root, and times the quantity cosine of pi plus 2 pi k all over 3. And for some reason I realized that these n's look like h's, so little n, little n. Okay, there we go. Parentheses plus I sine of, again, the same thing, pi plus 2 pi k all over 3. All right. And the solutions, they want them as a plus bi. Okay, so we're going to have to simplify all the way. Alrighty. And so we have x is equal to, and again, the cube root of 125 is just 5, because again, 5 to the third power is 125. And then let's simplify this, is going to be cosine, and then I'm going to simplify this a little bit further. It's going to be pi over 3 plus 2 pi over 3 times k, just to make it easier for us, and then times I plus I sine of pi over 3 plus 2 pi over 3k. Because again, we just want to plug in values of k and make our lives a little bit easier here. And so remember that my power, we're looking for the cube roots, so my k is going to go up to 2. So k equals 0, 1, and 2. Okay, so we're going to let k equals 0, 1, and 2. Because again, my n is to the third power. My n is 3. Okay, so now we plug things in here. So we have, okay, so here we go. This is for k equals 0. So we have x is equal to 5 times cosine of pi over 3, because again, k is equal to 0, so that we don't have to worry about that part, plus I sine of pi over 3. So that's going to equal to 5, and then cosine of pi over 3 is going to be 1/2 plus I, and sine of pi over 3 is going to be the square root of 3 over 2. And so this is just going to be 5 over 2 plus I, 5 square root of 3 over 2. Okay, we can actually put the I in the back here just to have it in that format. All right, so that's going to be one of the solutions here, one of the roots. All right, now let's plug in k equal 1. So we get x is equal to 5 cosine of pi over 3 plus 2 pi over 3, because again k is equal to 1 here, plus I sine of pi over 3 plus 2 pi over 3. And so that's going to be 5. And here we're going to get actually cosine of 3 pi over 3, which is just pi. So cosine of pi is just going to be -1. And then sine I, and then sine of pi is just 0. And there it is. That's the real solution. It's just going to be -5. So remember I told you guys that -5 was going to be a solution. One. Well, there it is. It finally showed up. Okay, and the other two are complex. So let's plug in k equals 2. All right. And so we have x is equal to 5 times, and here's my equation here, times cosine of pi over 3. And again, k is equal to 2, which gives us 4 pi over 3, plus I sine of pi over 3 plus 4 pi over 3. And that's going to give us 5. And cosine of 5 pi over 3 gives us 1/2. And then sine of 5 pi over 3 is negative square root of 3 over 2. So I times negative square root of 3 over 2. So that's going to equal to 5 over 2 minus the square root of 3 over 2i. All right, so those are actually going to be the solutions to that equation. So let me write that down. So the solutions to x to the third power plus 125 is equal to 0 are, and again, 5 over 2 plus 5 square root of 3 over 2i. Oh, actually, I messed up on this previous one here. Again, I forgot to distribute that 5 to that last one. So this is going to be 5 square root of 3 over 2i. And so again, the solutions to x to the third power plus 125 is equal to 0 are 5 over 2 plus 5 square root of 3 over 2i, -5, which is again a real solution, and then our other complex solution is 5 over 2 minus 5 square root of 3 over 2i. So these three again are solutions to that polynomial of degree 3. All right, and again, how can we check? Well, we could actually plug this back into my equation, simplify it, and we'll get that the left-hand side is equal to the right-hand side. Let's do one more example. Okay, and again, hopefully you're getting the hang of it. And again, if not, you guys can always reach out to me, and I will help you guys out. So let's just do one more. So find all the complex solutions to the equation and express the answers in a plus bi. Okay. So here's my equation, and it looks pretty similar to the previous one. And again, so we have x squared plus 2i is equal to 0. So I'm going to start by solving for x. So we get x squared is equal to -2i. And again, in order for me to to solve for x, I have to take the square root of both sides, which gives me this plus or minus, right? Plus or minus square root of -2i, which is the same thing as plus or minus -2i to the 1/2 power. And again, isn't this what we were doing this whole time? How to find the nth roots of a complex number? This is exactly what we were talking about. And so here, that's my n, that's my nth root. So we're looking for the square roots. Okay, the nth roots, the square roots of a complex number, where my complex number is right here. That's my complex number. And this here is my root. My nth root here would be the square root. Okay, so here, let me write it down. So we're looking for the square root, the square roots of negative 2i. All right, and again, those are going to be my solutions to this equation. All right, so here we go. Again, for step 1 is to write negative 2i in trig form so we can actually use that formula. And so let me just, again, if we actually, since this here is very nice, it's only the imaginary part, it's going to be easier for us if we actually just plot it, because again, negative 2i, that's going to be just on my vertical axis here. And so negative 2 is just going to be down here. That's my point right there. And so notice that the distance from the origin to that point is just 2. So my r, I already know that that's going to be 2. And my angle, again in standard position, my theta here is going to be 270 degrees, or 3 pi over 2. Okay, so sometimes it's nice to just graph it, especially if you're only given the real part or only the imaginary part, because it's going to be on one of the it's going to have a quadrantal angle. So but again, it doesn't always have to be that way, and then we already have the formula on how to find the modulus and the argument. So just giving you little tips here and there if you encounter some of these problems. Okay, so we already have it in that we already have our r and we already have our theta. And so step number 2 is to plug it into the formula. So just to remind you of what that looks like, it's going to have r to the, again, whatever the root is, here's the square root, so 1 over n, which again, n is 2 in this case, and then times cosine of theta plus, again, it doesn't always have to be theta, it could be another, alpha, whatever you prefer, but again, I just have it as theta in the formula, plus 2 pi k all over little n, plus I sine of theta plus 2 pi k all over little n. And so let me ask you this. What is, up to what value is k going to go up to? So remember, goes up to n minus 1. My n is 2. And so it's going to go up to 1. And so my k is going to be 0, 0 up to 1. So 0, k equals 0, k equals 1. And again, my n is 2, so we're going to have plug in two values of k, so 0 and 1. All right? And so again, k is equal to 0, k equal to 1. We're going to have to plug it into there. So let's do it. So again, these are solutions for x. So x is equal to, and then again, my r is 2, my n is 2, so 1 over 2. So we take the square root of 2 times, and then here we have the cosine of my theta is 270, or we can write it in radians, 3 pi over 2 plus 2 pi k, and my n is 2, because again we have the square roots, plus I sine of that same quantity, 3 pi over 2 plus 2 pi k all over 2. So again, before I actually plug in values of k, I'm going to clean this up a little bit. So I get x is equal to, and again, this is just the square root of 2, times, this would be cosine of 3 pi over 4 plus pi k plus I sine of 3 pi over 4 plus pi k. Alrighty, and so now it's time to plug in the values of k to find our roots. So k equals 0, let's do that one. So x is equal to the square root of 2 times cosine of 3 pi over 4. Because again, k equals 0, that eliminates that pi. plus I sine of 3 pi over 4. So this is going to equal to the square root of 2 times, and again, 3 pi over 4 is going to be, cosine of 3 pi over 4 is going to be the negative square root of 2 over 2, plus I sine of 3 pi over 4 is going to give us a square root of 2 over 2. And so if we distribute that square root of 2 to both of these, we get negative 1 plus 1. Oh, plus 1 times I. So it's going to be negative 1 plus I. All right, now let's plug in k equals 0. Oh, k equals 1. We already plugged in k equals 0. K equals 1. So we get x is equal to the square root of 2. And then now we have cosine of 3 pi over 4 plus pi this time, plus I sine of 3 pi over 4 plus pi. All right, and so again, 3 pi over 4 plus pi, that's going to give us 7 pi over 4. Here, I'll write it out just to have it here. So this is the same thing as cosine of 7 pi over 4 plus I sine of 7 pi over 4. And again, that's going to equal here. Let me finish that up down here. So this is equal to, again, the square root of 2. Cosine of 7 pi over 4, that's just going to equal to the square root of 2 over 2, plus I sine of 7 pi over 4 is negative square root of 2 over 2. So we clean this up a little bit, and x is equal to 1 minus I. All right, so again, we have our second solution, and actually that's it. That's it. We just we wanted to find the square roots of that complex number, and that's it. Those were the two roots. So again, if we plug those into original equation, it's going to satisfy it. So let me write that down. Actually, why don't we plot them? Since these are actually nice little numbers, so that you can kind of see again that they're supposed to be equal distance from each other. And so here, let me write as just checking. So checking graphically. All right, so we have so this is again our first solution was negative 1 plus I. So negative 1 plus I, so that's going to give us a point here. And then 1 negative I is right here. So notice that again, these are equal distance from each other. Okay, so again, this would be A, this would be B. You don't have to do this. Again, on your homework or anything, you don't have to do it, but I do want you to be aware that you can check your answers graphically. All right. And so let me just write it out. The solutions to x squared plus 2I is equal to 0 are negative 1 plus I and 1 minus I. All right. Well, thank you for sticking around. That was the end of 6.3.